Okay.
Okay, perfect. So, okay, today's lecture is a continuation from last time, and it will be a little bit short, but again, take advantage of the extra time to work with your team. So, if just to review what we covered on Tuesday, is basically we talked about the differences between non-imaging optics and imaging optics. The basic difference being that in non-imaging optics there is no one-to-one correspondence between a point on the object and a point on the image, whereas in an imaging optic there is this one-to-one correspondence. Okay, that's kind of the fundamental difference. Now, which makes the design problem in non-imaging optics much simpler. So the second thing we learned in terms of the concept is this idea of the edge ray principle. And this idea is relatively simple. The idea is that if you can take the extreme rays that you want to try to collect and send those extreme rays, there are two extremes, let's say in a two-dimensional case, and send those extreme rays to the extreme points of your receiver, then that ensures, and design your optical system to do that, it ensures that any rays in between will end up on the receiver, in between those extreme points. This is so-called edge ray principle that actually helps quite a bit. And we'll look at some example of how to use that today. Now, then we talked about the CPC, or the compound parabolic concentrator, which is a good example of a non-imaging optic and one of the, I would say, the most efficient solar concentrators that can be designed. Okay, so, and then we talked about how to design it, and it's made up of two paraboloids, so in two dimensions, two parabolae, which are reflected about an axis. Okay, so today our goal is to kind of delve a little bit deeper into the details of the CPC. So in the last class, just to review, this is somewhat important, is we looked at these two things. First, that in a CPC, the concentration factor, which is defined as the area of the receiver, which is this line right here, divided by the area of the input aperture, which is defined by this region right here, is given by 1 over sine of the acceptance angle, or half acceptance angle. Okay, this is A2, sorry, A1, which is the entrance aperture, divided by A2, which is the exit aperture, is 1 over sine of the half acceptance angle. Now, this is again a very important concept, and we proved it, derived it here. Essentially, what this says is that if you want to, and if you want to increase my concentration, so A1 over A2 is of course a concentration factor, right? So this is the size of your solar cell. This is how much your entrance aperture is, how much light you're collecting. So ideally, you want the solar cell to be as small as possible to save costs, and you want your entrance aperture to be as large as possible in order to collect more energy. So this ratio then represents what we refer to as concentration, or technically geometric concentration. We'll talk more about this later on. So that is inversely proportional to sine of the half acceptance angle, which means that if I have a concentration factor very small, let's say 2x, then the acceptance 1 over sine theta becomes very small, and sine theta becomes large. In other words, I can collect very large range of angles. On the other hand, if I want very huge concentration, let's say 1000x, that means this sine theta now becomes very, very small. That means I can only collect a very narrow range of angles coming from the sun, which means as the sun moves, it'll quickly fall out of those range of angles, which means that I need to track the sun much more precisely. Okay, so that's the fundamental concept, and it's a fundamental limitation, which in fact comes from the first law of thermodynamics. We'll talk a little more about this later on, but in fact, in today's lecture. So the other geometric constraint we talked about is the size of the CPC. So if I asked you to design a CPC, you will have to, what does it mean? That means you need to design A1, the entrance aperture. You need to design A2, the exit aperture, which of course might be given to you because that's the size of your solar cell, for instance. And then the next thing to design is the concentration factor, and then how tall is this, right? So you need to know how big this CPC is. And that h, which is the height of the CPC, is simply given by a1 times 1 plus sine theta over 2 tan theta, again inversely related to the half acceptance angle. Okay, so the more the concentration, the lower theta is from the previous slide, the larger h is. Okay, so ignore this first line, which is a typo. The second line is correct. As theta becomes very small, you're getting very high concentration, h becomes very large, so your CPC gets big, which is problematic, of course, because that means you have to track something very big and bulky, right? Okay, so those are the key trade-offs to keep in mind from the last lecture. Now let's think a little bit in detail at the, what are the, how does the CPC behave, and why do we say it's the best possible design, and so on. So let's try to answer the second question first. We claim in the last lecture that the CPC maximizes concentration. In other words, this is the best you can possibly do. So to show this, and which is, we refer to thermodynamics, and this is true in most situations related to solar energy. If you want to show that, think about the limits, what's the best thing you can do, you always start with thermodynamics. Okay, and we start with a toy problem, something very simple for us to model, simple from in concept to understand. Okay, so we consider first a cylindrical black body at some temperature T, and imagine this is a cylinder which is infinitely long. Okay, so it's just a line. Okay, it has a radius of r, and we'll look at a little segment of the cylinder whose length is Lu. We will later on put this as 1, but let's just say it's Lu, and we call it SR. Okay, so this is drawn in 3 dimensions. Now, our in this particular situation, this is situated in vacuum of space, which is at 0 Kelvin, and then far away at some distance d, we place this linear concentrator. So this is a linear CPC, which means it's a 2-dimensional CPC shown here. The entrance aperture is on the left, the exit aperture is on the right, but it's infinitely long. Okay, so it's a linear concentrator with a concentration factor of C. C is essentially the ratio between the entrance aperture divided by the exit aperture. Okay, so far it's pretty straightforward. Okay, the question we want to answer is how much energy reaches the exit aperture of this concentrator. Okay, that will help us understand what is the best concentration efficiency one can hope to achieve. So in order to do that, because this is a cylinder, we'll look at a cylindrical surface. Okay, with a radius of d. And the reason is because this is a cylindrical object, it's emitting light in all directions in a cylindrical shape, right? Because it's infinitely long in this direction. As it emits light, the light moves in a cylindrical wavefront. Now, this is a black body at temperature T, so it emits radiation, as we know, and we can compute its total flux. So the total flux emitted by a black body, and we'll look at a small area of it. So dA, let's just pick a small area on its surface, dA, and it's at a temperature T into a hemisphere is given by d of flux phi is sigma T raised to 4 dA. Now this is of course the Stefan-Boltzmann law, sigma being the Stefan-Boltzmann constant, T being the temperature, so we know this from Stefan-Boltzmann law, and then dA is just the area. So you multiply area by the flux density, you get the total flux. Okay. So that's what's coming out of the cylindrical black body. Now, we are going to say, we will look at a length Lu. Okay, our black body, let's say we have a little segment here of length Lu, and it will emit, essentially, we take this dA and write it by the surface area of the cylinder of length Lu, which is 2 pi r times Lu. So dA is nothing but 2 pi r times Lu, which is the surface area of the cylinder, right? R is this radius of the cylinder right here. Okay, simple so far. So we basically have the total flux is 2 pi r Lu times sigma T raised to 4. Now, because we are saying that this is an infinitely long cylinder, we're going to make Lu equal to 1, which means that we want to know what's the flux per unit length. So every unit length of this source, how much flux is coming out. So flux emitted per unit length, where we just simply said LU equals 1, is given by 2 pi r sigma T raised to 4. Okay, so what is this? This is the flux, which means it is the power density coming out as a function. Sorry, it's not the power density, it's the total power coming out of this black body. Of course, this is it is coming out in a cylindrical wavefront, but it's given by 2 pi r sigma T raised to 4. Okay, now that's the total flux coming out. Now the question, of course, is coming out as a cylindrical surface. Now the next thing we need to calculate is how much flux is actually incident at the entrance aperture of the CPC. Okay, so in order to calculate that, we will take a two-dimensional cut of this three-dimensional picture, which is shown here. Okay, this is much simpler to see, right? So this is our big cylindrical source. Okay, radius r. At some distance d away, we have our CPC shown here. Again, this dashed line shows the cylindrical wavefront. Okay, and let's see. So this is the temperature T. This is the concentration factor C. Okay, so again, our question is how much flux is incident on the entrance aperture of the CPC. Okay, we also have this angle theta. You can see it's just represented by the edge rays of the source, right? So this theta now represents the extreme ray of light that can come from the source to the CPC, right? We picked the center of the CPC, but you can see as you move it around, this theta doesn't really change very much as long as D is very large. So we can just pick the center. So theta is kind of the edge ray, right? This is defined by the edge ray. Okay, so the amount of radiation, the entrance aperture A1, which is right there, receives per unit length of the source, that's the source, is the flux, which is the total flux coming from the source, which is the numerator here, sigma T raised to 4 2 pi r. Okay, this part right here. Okay, divided by 2 pi d. What does that mean? That is, d is of course this distance, and that is the surface area of the cylinder defined by these dashed lines. So that's the big area over which the entire light or the heat emitted by the source is distributed over, right? It's uniformly distributed over a huge hemisphere here. And that's the 2 pi d times 1. Again, we are looking at unit length, is the surface area of that hemisphere. So if you take the total flux from the source divided by the surface area, you get flux per unit area. So that's what's per meter squared so far, right? Actually per meter, because we're doing it per unit length, but that particular distinction is not so important because these things are infinitely long. Okay, then we take that flux density and multiply it by the area of the CPC, entrance aperture of the CPC. That gives us how much flux enters the CPC. Okay, so A1 is basically the one-dimensional area or the length of the CPC. Again, we are assuming unit distance or unit length in the dimension into the plane of the screen here. Okay, so this flux now gives us how much power is entering the CPC from a source of temperature T, which is at a distance d away, and whose radius is r. Okay. Okay, so far it's relatively simple. Now we have to start applying some thermodynamics. Okay, of course, Stefan Boltzmann law is from thermodynamics, but now we're going to assume some interesting abstract concepts. So let's think about this carefully. Assume that there is a black body that absorbs radiation at the exit aperture A2. So again, we're trying, the goal here, this is a concentrator that collects light from A1 and sends it to A2, shown here. And let's just assume there is something here, and that something can be a solar cell, a perfect solar cell, let's say, which basically acts like a black body, and it absorbs everything that comes in. Okay, so that's an ideal black body. Okay, the temperature of this something here, in general, will have to be less than the temperature T, less than or equal. We'll come to that in a second. Okay, and the reason is, of course, this is our universe now. There's nothing else in here. There's something at temperature T. Everything else is at 0 Kelvin. And this is our little absorber here at some temperature, which will be higher than 0 because it's absorbing energy. But it cannot be higher than T because it's the only source of energy. Okay? But at thermodynamic equilibrium, what is important is that the temperatures have to equalize. What does that mean? That means that the temperature of this and the temperature of the black body that's absorbing has to reach a thermal equilibrium. And this is a big assumption, right? Of course, a solar cell is not the same temperature as the surface of the sun. So that's obviously one of the reasons you can imagine why the solar cell does not reach like the Carnot efficiency, right? Anyway, we'll come back to those concepts later on in the second half of the class, but just keep that in mind. So here we're making a very big assumption. It's an abstract assumption, but it's useful to understand the limits. The temperature of this black body has to be less than T. That is correct. That's not a big assumption, but the big abstract assumption is that at equilibrium, this will be equal to T. So in other words, you have an absorber here, which is the same temperature as this. Now, what does that mean? Now, if you have an absorber here, which is the same temperature as this, and it's a black body, of course, it also has to emit light, right? It also has to emit radiation because it's a black body. Anything that absorbs light also has to emit light, right? From thermodynamics, again. So it will also emit radiation with a flux per unit length given by its temperature, right? Sigma A2 T raised to 4. Now, of course, now the big difference is A2. Right? Sigma T raised to 4 is the same because it's the Stefan-Boltzmann law, but the only difference is it's smaller, right? Its size is A2 times the unit length. Okay? So that's what's coming out of this black body. Now, if we make one more kind of, let's say, radical assumption, is that, of course, there's nothing else in this universe. That's our entire universe here, which means that any radiation that this emits, this black body emits, the only place it can go to is the source, right? It cannot go anywhere else. There's nothing else to go, right? So there's no other black body, essentially. The CPC is not a black body. So like we're going to assume this is perfectly reflective, right? We haven't said anything about its geometry here. So what that means is that the flux from here, the only place it can go is here. That means, and it's a thermal equilibrium, the flux leaving this black body receiver should be equal to the flux entering from here into the CPC. Okay? Again, we don't need to say this is a CPC because that geometry is not important. Some concentrator, let's call it. Okay? So the flux entering that concentrator must be equal to the flux leaving that concentrator. Otherwise, it won't be thermal equilibrium. Otherwise, its temperature of this black body will start changing, right? It'll go up or down. So this is a very important concept in thermal equilibrium. And most importantly, keep in mind, we have made no assumption as to what the geometry of this concentrator is. Now, if you simply apply this equation, which means you take this and put it equal to this, you get a very interesting expression. You get A2 over A1, which is the concentration, A2 divided by A1, is 1 over the concentration, is simply given by R over D, R divided by D, which if D is large enough, is the same as sine theta. Okay, or in other words, what we have shown with the very simple thermodynamic arguments is that the concentration factor of this concentrator, we haven't said it's a CPC, it can be anything. The best concentration factor one can hope to achieve is 1 over sine of theta, where theta is the angle of the extreme ray. Okay, so it's kind of a profound conclusion where we only made thermodynamic arguments to come up with this conclusion. Okay, now of course from our previous analysis, we know that the concentration factor of the CPC follows the same relationship, which means that the CPC is actually the best one can do thermodynamically. Okay, I'll repeat that. So let's just complete the argument first. So since in our universe the rest of the space is at 0 Kelvin, radiation leaving A1, which is the open area of the entrance aperture of the CPC, and coming from A2, which is the only black body on this side, the only place it can go to is the source, SR. Okay? This implies that the acceptance angle of the CPC with entrance aperture A1 cannot be larger than theta. Right? Which of course is obvious, because anything that leaves here, there's nowhere else for the light to go. It can only go here, which means that any light that comes in or leaves must have an extreme angle of theta, right? Because there's nothing else. So as d goes to infinity for a given theta, okay, right? R goes to infinity, which means that this object becomes huge, okay? Then A1 becomes a straight line, which means that this cylinder, this arc of a cylinder now becomes a straight line, and the concentration factor simply becomes A2 over A1 equals 1 over sin theta, which is the same as what we just said. Okay. Now, the profound conclusion is that in 2 dimensions, because why is this 2 dimensions? Because we assume that the source and the CPC, everything is linear, right? We assume that in the 3rd dimension it's infinitely long. So we didn't care about the 3rd dimension, which means that we are just thinking this is a 2-dimensional universe. The profound conclusion is that in 2 dimensions, the maximum possible concentration, independent of what you do, is always limited by 1 over sin theta. There's nothing you can do to go above it, because otherwise you'll break the 2nd law of thermodynamics. Okay. Now we also know this is the same concentration that is achieved with the CPC, and based on just this equivalence, we can conclude that the CPC gives the maximum possible concentration in 2D. So that's kind of a trivial conclusion, obviously. Okay. So it's a little bit abstract, but it's important that you think through it and appreciate the logic of how we come to this conclusion. Okay, and I'd like you to go back home and think about this a little bit. Again, the mathematics is almost trivial, the geometry, but it's the conceptual understanding of why we are saying this, why we are reaching this conclusion that's important. Okay. Now, of course, our universe is not 2 dimensions, it's 3 dimensions. So we need to actually consider that. And it changes things, so it's important. So in 3 dimensions, of course, our source is now a sphere, like our sun. It's a huge sphere, let's say, again, SR, at some temperature T. And now we have some concentrator. We don't need to say it's a CPC. Some concentrator on Earth. As shown here, which is an entrance aperture area of A1, an exit aperture area of A2, capitalized both. And then the extreme rays now are there are 2 angles, right? One theta in this plane, another theta in this plane. And for symmetry, we're just saying they're the same. They don't need to be the same in actual practice for the sun. Of course, they're not necessarily the same. But for our purposes, we'll just say they're the same. So it's just a symmetric sphere, okay? Then we can work through the same arguments. The logic is exactly the same. Yeah, so let's go in this direction, okay? Yeah, so the flux emitted by the logic is exactly the same as before. The flux emitted by the spherical source is now given by the area of the source, which is 4 pi r squared times, 4 pi r squared. So that's the area of the source, right? That's the area of a sphere times sigma t raised to 4. That's what's emitted from the sun. Now, of course, we are looking at some distance d away, which means that we need to divide it by the surface area of this huge sphere over which the light is incident, right? So the radiation captured by the entrance aperture A1 is 4 pi r squared sigma t raised to 4, which is this, what's coming out from the sun, divided by the area of the huge sphere, 4 pi d squared, multiplied by the area of the entrance aperture A1, just like before, exactly the same expression as before. So 4 pi cancels out, and you will end up with r squared, t squared. Now, this energy is then collected by this concentrator here and assigned to some receiver of an area A2. Okay, and this is just the vertical cut, looks exactly the same as before. onto a black body at the exit aperture A2. At thermal equilibrium, we know that the black body here has the same temperature as the sun, or whatever the source is at temperature T, and the flux coming off this black body must equal the flux coming in at thermal equilibrium. And then you get this simple expression. So this is what's coming into the concentrator, 4 pi r squared sigma T raised to 4 divided by 4 pi d squared times A1. And that's equal to what's coming off the black body, A2 sigma T raised to 4. Now, T are the same, so cancels out, sigma cancels out, and you get a very simple expression, A1 over A2, which is A1 divided by A2, which is a concentration factor in 3 dimensions, is D over R squared. Now, D over R is nothing but 1 over sine theta. Okay, so now A1 over A2 is 1 over sine squared theta. Okay, so just think about that difference for a second. So in 3 dimensions, the concentration factor, the extreme concentration factor, so this is, what are we saying? We are saying what is the best possible concentration you can hope to achieve for a given acceptance angle, half acceptance angle. So theta, in this case, keep in mind this theta is the half acceptance angle. So I should have drawn actually half the arc here. So this is a typo again. So just keep this picture in mind. It's a half acceptance angle. So A1 over A2 is 1 over sine squared theta. So just to review, in the previous slide, we saw that A1 over A2 is 1 over sine theta in 2 dimensions. And in 3 dimensions is 1 over sine squared theta. So different, quite different. And this is why we said early on in the last lecture that in a CPC in 3 dimensions, this is no longer true. In other words, the concentration factor of a CPC in 3 dimensions is not 1 over sine squared theta, which means the CPC in 3 dimensions is not an ideal concentrator. Okay, which is why we said before, there are some skew rays that will escape the CPC. Okay, so, but this is still a very useful concept because thermodynamically, this is the best one can hope to achieve in 3 dimensions. That's why this concept is important. Okay. So a few things we can extrapolate from this. As D goes to infinity, which is basically this thing gets very far away, the R goes to infinity, gets huge compared to the concentrator, which is our situation, of course, at constant theta. Then A1, this entrance aperture becomes a surface, flat surface instead of being a sphere, right? Just like before. It doesn't really change our argument because we can assume all the logic that we said before is true for a very small, infinitesimally small entrance aperture here. So, and you can apply this over the entire sphere. So the argument doesn't change based on that. It's just exactly the same. Okay, so there's one other parameter that affects the concentration factor, which is the refractive index of the medium. So let me explain what that means. So in this example that we looked at, the black body is placed in vacuum, right? That was what we said, or in air or something. Air and vacuum are the same for our purposes for now. Okay, it's sitting right there, right? That's our solar cell. But what if this black body is sitting inside the CP or in contact with the CPC, where the CPC is not just a hollow material, but it's made of glass or plastic or something solid. So its refractive index is no longer the same as that of air or vacuum. Okay, turns out these equations change. In fact, they change because of fundamental thermodynamics. Okay, we won't go into the details. I'll briefly mention. So let's look at this first. If the black body is immersed in the concentrator whose refractive index is n, then what changes is actually the Stefan-Boltzmann constant, sigma. Sigma has this dependence of n squared. Okay, you don't need to know this because it comes from quantum mechanics. But essentially, this dependence of n squared, which means that sigma, the Stefan-Boltzmann constant itself, scales as square of the refractive index of the material. In other words, sigma in some material n of refractive index n is n squared times the sigma in vacuum. Okay, then we see, and the conceptual way to think about this is the following: when you have a material of a certain refractive index, it turns out that you have what are called density of optical states that are multiplied by a factor of n squared. And if you recall your undergraduate thermodynamics, this density of states determine how many optical modes can be supported. What that basically means is that you are able to essentially send in more rays of light to a material of refractive index n compared to vacuum. And you will see exactly what I mean in the next slide. But that's one way to conceptually think about this. So, but keep in mind our source is still in vacuum, so we can substitute all the equations. Now sigma becomes sigma v because of vacuum, so that's our source, which the flux from the source, which is reaching the entrance aperture of the concentrator, and this is what's leaving the concentrator because of the black body of the receiver. And you get a simple expression here, a1 over a2, which is our concentration factor, is now n squared divided by sine squared theta. Okay, so instead of just having 1 over sine squared theta, now you have an n squared term in the numerator, which is very important, right? Because n can be a relatively large number. It can be, for glass, it's 1.5 roughly, changes wavelength. But let's say for silicon, it's about 3. So n squared is a factor of 9. So, that's a pretty big number. So which means that you can increase your concentration factor by that number, which is nice. You can take advantage of that. In 2D, you can do the same analysis and you'll end up with the expression that concentration factor is n over sine theta. Okay, so slightly different. Now, how do you think, of course, these are just equations, which are important, but how do you think about this conceptually? It's actually quite simple. The picture is here. So imagine your CPC. Let's take the CPC as an example. It doesn't need to be a CPC, it can be anything. If you had a material, a refractive index n, filling the CPC, instead of air. So previously we talked about the CPC as being hollow, right? There was nothing inside it, was just reflective surfaces on the surface. But imagine that this is a big piece of glass in this shape, okay? And this reflection is total internal reflection, as you learned in your lecture on geometrical optics, right? That can happen. So then the incident angle, let's say here is theta, okay, to the normal. It will refract by Snell's law in here, by theta star, such that sine theta is now n times sine theta star. So you can see what's happening. I can take a large cone of angles in air and compress it into a smaller cone of angles inside the glass. So in other words, I can take this large number of rays, because of this range here, and compress them into the same number of rays, but now compressed in a smaller region. This is what I said before, that the density of optical states have increased. And this simply comes also from Snell's law. Okay, all of their expressions are the same, which means that a1 sine theta star is now a2, which we derived before. Nothing has changed. All the geometry is exactly the same, which means that a1 over a2 is now n over sine theta. So it's a very, very simple derivation using simply Snell's law, right? Not even thinking about thermodynamics. Okay, so this is, of course, a nice way to take advantage of, one can take advantage of this in order to increase concentration factor more than one is generally allowed to do in air. And I won't go into much detail, but there's a very nice paper from the 1980s in Nature where they essentially concentrated sunlight. So the title is Concentration of Sunlight to Solar Surface Levels using non-imaging optics. So in other words, they concentrated the light and heated something up in their receiver. It was not a solar cell, it's just a receiver, so a black body, up to a temperature which is higher than the surface of the sun. And the way they were able to achieve it was by immersing that object in a refractive index n, which is greater than 1. In their case, it was gallium arsenide, so which is refractive index is pretty high, like 3 or 4. So that's a clever idea. So their system is shown here, which is of interest to us. So sunlight comes in. They had a reflective mirror here, okay, which focuses, mirror lens. It focuses. And then they have a secondary non-imaging concentrator down here, which is not really shown in detail, but you can think about it like a CPC. And that CPC essentially, it's shown as a lens here. So basically collects the light and focuses down to essentially calorimeter. So it's an oil-filled calorimeter that's heated up, and they measure they have a very precisely calibrated heater here, which allows it to measure the temperature with these thermocouples. So the image of the sun is formed here. And because this whole thing is inside the oil, you get higher refractive index. Okay. It's an interesting example. One can think of taking advantage of it, for instance, by using water or whatever. Of course, this is a very difficult experiment to do because you need to cool it very carefully. These things can get damaged because of the huge concentrations involved here. Okay, so with that, that ends kind of our overview of non-imaging optics. So that's all I will expect you to know for the midterm from a non-imaging optics point of view. So at this point, I want you to spend like 5 minutes or so, and the TA is going to walk around. I want you to solve this problem. So talk to your neighbor and design from everything you've seen so far, and you can think broadly as well. Design a concentrator that can concentrate sunlight into a ring of light. Okay, and you also have to think about, is that a non-imaging optic? Is that an imaging optic? What is it? Okay, and I want you to spend a few minutes on it. So I'm going to let you discuss within yourself, and excuse me, have the TA walk around and discuss with you. And at the end of a couple of minutes, I'd like a couple of you to draw your solutions on the board and explain it. Okay? Okay, why don't you get started?
So basically, like it lens the that class is probably circle. So you have like I don't know.
Any solutions so far?
Yeah. So one.
Okay, so
Can you see?
yes, I can see, yes.
So just a conical mirror in the middle. So you have a donut parabola.
So you have a kind of like a reflective surface right at the center.
Right, yeah.
Okay, yeah, perfect. Yeah, that was what I would have solved as well. And any other solutions? That's pretty good. Of course, to make this will be very complicated, so it may not be the best solution, I suppose. But anyone else?
So this is oh, yeah, but I mean, obviously, this red green. So, yeah, it would be he's like that. He's like the center. He's like a reflection. So sorry, like you said, this would have like a little block center, right? We're just rejecting.
Anything else? No? Anyone else want to draw another solution, or so far? No? Okay, yeah, I'll let you think about this. Let's try to finish the rest of the lecture. But the answer would have been very similar to what I would have come up with, is similar to what you did. So that's good. I'm glad you're paying attention. But of course, there are many ways to do this. And you might wonder, why do this? It turns out, I hope one of the teams will look into this, but there is there is a technology which is very low tech, but it's used for refrigeration, water cooling, called the Zeripot or Zeropot. I forget the exact name. But in that particular case, you want to have a situation where you want to concentrate sunlight, but you don't want any power in the center of the geometry, because you're putting something there to cool. So this would be an example of where concentrating sunlight to a ring would be important. Okay, so let's talk about one other problem, which is very important, related to concentration, which is tracking the sun. So I want you to pay attention to this very simple demo of a tracker, which is interesting because it uses solar energy in order to track the sun. In other words, what it means is that typically you want to run a motor, but if you can use, and you need to expend energy to run that motor in order to track the sun. But if you could use the sunlight itself to track the sun, which is, for instance, what a sunflower does, right? It uses sunlight to track the sun. That would be a very elegant solution. This is an example from I think it's a middle school student, but let's take a quick look, and I'll try to fast forward through some of these things. But I like this because it's very simple. I won't play all of it, but the idea is that
This is solar panel that we'd like to use in the sun. This is a turntable, the type you find in restaurants. And these are two solar cells and a small motor taken from point to point. This is how my device works. When the sun hits this solar panel, the motor will turn the turntable this way. And when the sun hits this solar panel, the motor will turn the turntable that way. And when the motor is stopped working, it's when the sun is aligned in the middle. This is a small motor connected to this solar cell. And this is how our idea works. And this is now to Flux. And when we reverse the wires, this will be now turning counterclockwise. And this is what we used in our project. I hope you like our idea.
Okay, I'll stop there, but you get the idea. So that's a very elegant, simple solution, but of an important problem. Obviously, there are lots of details here, but we won't go through it right now. But you can think about things. How would you improve this? So, for instance, for the teams who are interested in using concentration to improve the performance of whatever device you're working on, you have to worry about how will you track the sun, right? Or if you don't, then you have to say, okay, we're not going to track the sun, and that will take the loss involved with that. But if you're going to track the sun, then you need to address, how will you do it in a cost-effective, simple, reliable fashion. So that's my question here. How would you improve on this? But the idea was for you to brainstorm, but we don't need to do that right now. I want to show you one more tracker, which is quite different, completely different configuration. This is for heliostats, not for exactly tracking the panel itself. And this is a video from an innovation summit from a few years ago from an agency in the US Department of Energy called ARPA-E, which is basically an advanced research projects agency for energy. Okay, so let's take a quick look.
Well, everyone wants solar energy to be cheap, but right now it's not. And one of the reasons is for the concentrated types of solar, you basically have a robot that has to point these solar panels or these mirrors at the sun to very high accuracy. And when you do that with metal and motors, at some point it ends up that the solar, it's not really a good trade-off to do solar anymore because you're using so many resources and you're doing it so extensively. It's not really accessible to most of the world. So we're working on a new form of solar tracker that's based on plastic and water actuators as opposed to the traditional metal and motor-based actuators. This is the actuator we're basing our solar trackers on. We call them heliostats because they follow the sun. Over here we have a very small-scale version of our array, and our actual array would maybe have 100 mirrors this size. And these mirrors are much smaller than what's out in the field right now, and there's a lot of advantages to that. One of them is the closer you get to the ground, the less wind loading is a problem. And because it's so lightweight, we could start thinking about putting concentrated power on rooftops, places where we haven't been able to do it before because it's such a heavy system. One of the mirrors on this array is demonstrating movement, and the movement is happening just by distributing water to each of the chambers. Instead of having a motor on each of these, instead you'll have a centralized control system that just routes the fluid where you want it. So you have one small control system that can control up to 100 or more of these in the field, which makes the cost of control very low. There's very few people doing robotics that is fluid-based, and definitely no one in the solar industry is doing hydraulics this way. Well, if everything's successful, we're introducing something that could make solar energy at coal parity cost. So solar power could actually be as cheap as any other form of energy, which would be very enabling.
Okay, so that's a different, of course, it's a different approach, as you can tell. It draws inspiration from the sunflower, for instance, and the way the sunflower actually moves is by fluids. Of course, in that particular case, there are proteins involved, which does the signaling. But anyway, so that's an interesting approach as well. And the last thing I would say is take a look at this TED Talk, which I've linked to on the website by Bill Gross, and because he actually talks about a different form of non-imaging optic for solar, the tracking and so on, and it's actually quite powerful. So I would recommend it. With that, I'll stop and.